Hello, hello. Today we are going to talk about work, power, and machines. This is all still in Chapter 8, Energy, and today's topic is Section 8.7, Simple Machines. But before I start to talk about machines, let's do some review. We're going to review work and power. So, what is work? The physics definition is the product of the force and the distance. So let's ask some questions. These were supposed to be animated. If you are pushing the lawnmower around the lawn, is that doing work? Yes. You're applying a force to the lawnmower and it's moving across the lawn. If you are lifting weights, is that work? Yes. If you're moving furniture up a flight of stairs, yes. You're carrying that furniture up against the gravitational energy. What about pushing it against a locked door? No. Swinging a golf club, that is doing work. You're applying a force to the handle and the golf club is moving through a distance. But why is pushing against a locked door not doing work? Because if all you're doing is standing there pushing and the door is not moving, then if the door is not moving, then the distance that the door is traveling is zero. So if you take any amount of force and multiply it by zero, you still get zero. So remember, this is a scientific definition. This is physics class. And work, you may understand work to mean a lot of things, but in the scientific world, work means force times distance. And so if you don't have a distance, you're not doing any work. So do you do more work when you finish a job quickly? We'll talk about that, an example for that in just a minute. But I want you to realize at this point that work does not involve time, only force and distance. So there's the equation. I wrote it out for you. Work equals force times distance. We measure force in newtons and distance in meters. And if you remember, a newton is a kilogram meter per second squared. So when you multiply all that out, you get what's on the bottom there. A unit of work is a kilogram times a meter squared, all divided by second squared. And what do we call that? The joule. 1 Newton meter is a quantity known as a joule. It was named after James Joule, seen right there. We've seen his picture before. So next topic after work is power. They're closely related because power is how quickly work is done. The scientific definition for that is the amount of work done per unit time. Now, 90% of the time, our unit time is a second, but you can talk about it in terms of minutes, hours, days, weeks, even centuries. So if two people mow a lawn, or two lawns that are the same size, and one does the job in half the time, who did more work? The answer is they did the same amount of work. Because if you're pushing the lawnmower and you have to go back and forth so many times, you've applied a force over a distance. Now, both those people applied the same force over the same distance, so they have the same work. Now, the person who pushed the mower faster did the job in half the time. So power at the bottom there is work divided by time. So if you do the same amount of work in half the time, do you see from algebra that that means that you have twice the power? So the person who did the job quicker has more power. They're more powerful. Another way you might think of that is strength. Now, we don't have a scientific definition for strength, but it is similar to power and in the English sense of the word. But power definitely has a scientific definition. There it is. And if we take that work, which is a joule, and divide it by time, which is a second, what do we get? The watt. That was named after James Watt, who was famous for inventing, that slide is wrong. He didn't invent the steam engine, he invented a better steam engine. And there are the units. Power equals work divided by time, which is joules per second. So 1 watt equals 1 joule per second. Watts Watts are commonly used when we talk about how bright a light bulb is. Another place you might see watts is on an electric bill. That's measured in kilowatt hours. Um, there's kilo and megawatt down at the bottom, abbreviated KW and MW. And another way to measure power is horsepower. As anybody who's shot for cars or thought about your 0 to 60 time, horsepower is important. Um, 745 watts equals 1 horsepower. So, a horse can pull a load of, in the picture down below, at 167 pounds. The 1 horsepower can move that object 1 foot or in 1 second. I'm sorry, 1 meter in 1 second. Now we're moving on to machines. So, what is a machine? Oops. The first thing I think of when I think of machine is that Terminator movie, Rise of the Machines. Um, and oh God, that's probably too old for y'all to remember. Um, but normally, when people think of machines, they think of something big and very sophisticated. But a simple machine, the most basic machine, is actually very simple. And the basic idea is a machine is something that we use that makes getting work done easier. So, what does that mean? So, if I'm a human being and I'm trying to get some work done, I'm trying to push something. If I'm exerting work, a force, and I'm moving the object, then a machine can change the size or the direction or the distance over which the force I'm applying acts. That doesn't probably make sense right here, right now, but let me get through some examples, and that will definitely make sense soon. That line is also definitely in your notes. So if there's a machine, then it doesn't work by itself. I have to do some work to it, or something has to do some work to it. In the most basic examples, it's usually a person doing the work. So I am doing a force onto the machine. We call that the input force. That's the force applied to a machine. And then the machine does something, does its little machine thing, and then the machine outputs a force. And that output force is the force applied by the machine. So there are two forces, and therefore there are two types of work. There's the work input, that's the work done on the machine, and the work output, that's the work done by the machine. Now remember, work has a scientific definition. It's force times distance. So if I'm inputting a force and it's moving through a distance, then the work out of the machine is going to follow the same equation. The output force equals, the output work equals the output force times the distance that the machine moves it. Did that make sense the way I talked through that slide, the two columns there? So then the question is, can you get more work out of a machine than you put into the machine? This was supposed to be animated. And the big answer to that question is no. No matter how much work you put in, you can never get more work out. And we're okay with that because we designed the machine to suit the purpose. So we know how much work a person can put in and we know what we want out. So we just designed the machine to make sure it's going to do what we want. If that doesn't quite make sense yet, that's okay. We're only halfway through this. Okay, so what are these wonderful machines then? There are 7 of them. But really, they're all based on one thing that they all have in common. So at the end of this, I will ask you again to see if you can spot that one thing that they all have in common. And if you're not sure, I'll give you a hint. The wheel kind of is by itself. The other six, it's a little easier to see how they all have something in common. Okay, so let's get to it. Number one, the lever. Oh, where's the picture? There it is. Okay, so there is a lever. There's the guy standing on, if you look closely, you can see that's a steel beam, and he's got some wood piled up, and that's what the lever sits on. And then the other end of the lever is under the car. So all these parts have names. Um, the bar is the part of the lever that goes up and down, and it moves around a fixed point. That point is called the fulcrum. So in the picture, where the bar is sitting on top of the wood there, that's the fulcrum. So the bar on the left side goes down while the guy's standing on it. The bar on the right side goes up, and the fulcrum is the point that doesn't go up or down. There are three classes of levers based on the position of the force that you're applying, the output force, and the fulcrum. That's a little hard to see, but fortunately we have pictures. I wanted to go back to this slide because I fixed the definitions a little. So there are two parts to the lever, the bar and the fulcrum, and those are both underlined. But there's also the word pivot at the top, and the definition of the word pivot means that you are able to move around a fixed point. So the bar is the part that's free to pivot when an input force is applied, and the fulcrum is the pivot point of the lever. So then we're going to go on to the classes, three types of levers. The first class lever is what a class of first graders would call a seesaw, and that's fine. So there's the picture. You've got the fulcrum, and at the fulcrum is the point that doesn't move up or down. You've got a load on one side and the effort on the other side. So that makes the work easier by multiplying the force and changing the direction, because if you push down, then the load goes up. And that's easily seen in that classic picture of the two girls on the seesaw. And those girls are about the same size, but then in the picture below, there's the guy trying to move a boulder, and that boulder is much bigger and heavier than he is. But because he's using the lever, and it's much longer on his side, he's able to push down and lift the rock. And if you look at the picture on the bottom right, that's illustrating that. With a long lever, you can move a very heavy load. And in fact, among us scientists, there's a famous quote from Archimedes who said, if you give me a lever long enough and a place to put it, I could move the world. He's right. And then another example of a first-class lever is a pair of scissors. You just take two first-class levers, stitch them together at the pivot point, and bang, you've got yourself a pair of scissors. The next type of lever is the second-class lever. So on this one, you can see that the fulcrum is on one side, and then the effort and the load are on the same side. So when I'm pulling up on the lever, the load is on the same side and it's going up also. So the force is both in the same direction. When I pull up, the load goes up. There's a couple examples. The classic is the wheelbarrow. The point of the fulcrum is where the bar of the wheelbarrow hits the axle of the wheel. And you lift up on the wheelbarrow, and suddenly you can lift a pretty heavy load in that wheelbarrow. Then finally, there's the third class lever. And that is where the load and the effort are switched from the second class lever. So the effort is being applied close to the fulcrum and the load is far away. So this does not multiply the force. If you put in an effort, the Let's just go on to the examples. There's the classic example for third class lever. That's the arm on the left side of the picture there. So the muscle is attached to the forearm, and the point of pivot is at the elbow. So the muscle is pulling up on your arm, and then the load is, of course, usually in your hands. So that's the classic third class lever example. Other examples are also a bat, a baseball bat. It's not attached to the pivot point, but the pivot point would be at the bottom of the handle, or a racket when you're swinging that around. Okay, so that was a lot. There were 3 classes of one of the simple machines, the lever. The good news is the next 6 of the list of 7 are all quite a bit easier. But first, I wanted to show the 3 pictures of the 3 classes of the 3 types of levers. So there they are. And I think once you see those 3 lined up together, then that whole idea starts to make a lot more sense. I should definitely get that into the notes. On to the wheel. There it is, a wheel. If you go back to the lever there, and if you look at class number 3, if you imagine that the bar is pulled by the effort, and instead the bar just goes around the fulcrum and goes all the way around, makes a complete circle. Well, if you do that, then you've got yourself a wheel. So you could call a wheel, as in the notes there, a lever that rotates in a circle, or you could just call it a wheel. If you take 2 wheels and stick them together and you want to attach them, then you need an axle between them, like in the picture. But even if you just have 1 wheel and you want to put a load on it, like a wheelbarrow, you need to have an axle in there so that you can attach the wheel to something. So there we go, the good old-fashioned wheel. Number 3, the inclined plane. So if you look at the picture on the bottom there, there's a guy who's got a load that he's pushing along. And if you had to lift that load up onto the ramp, up onto the dock, that could be very heavy. So instead, he rolls it up the ramp. And a inclined plane is the scientific word for a ramp. It's a slanted surface used to raise an object. Stairs count because rather than having to jump up one whole flight, you take a lot of little steps. Okay. Number 4, the wedge. Basically, a wedge is an inclined plane that moves. The classic example there is the axe. Now, if you sharpen the axe, then you can make a razor blade or a knife. And the trick of it is the sharper the edge, the easier the work is to do. And that is short and sweet, and we'll leave it at that. Number 5, the screw. So if you take a inclined plane and you wrap it around a cylinder, do you see what I'm saying there? There's the cylinder shaft in the middle of the picture on the top left, and then the ridge. Do you see how that rises up and just circles around the cylinder, just like an inclined plane? So once you wrap that inclined plane around the cylinder, then you have yourself a screw, and we call that a whole different simple machine. Then number 6 is another classic, the pulley. So a pulley is just a wheel attached to a stable object, and then you throw a rope over it and you can lift something else. The nice thing about that is if I want to lift in the picture, if you want to lift the boulder up, you can pull to the side. And then another clever trick with pulleys is you can use more than one. So in the picture on the left there, there's 1 pulley, but in the middle picture, there's 3 pulleys being used. And there, if you attach the load to the P on the bottom there, and the PA is where you pull. Well, now you can lift something that's twice as heavy as you are. And if you use a bunch of pulleys, you can lift something that's 4 times as heavy. Now, if you've ever done that, you know the trick is that you have to pull a lot of rope out. If you have 4 pulleys, then you have to pull the rope 4 times as long to get it to raise it up off the ground 1 foot. So if you want to raise the object 1 foot, you have to pull 4. Excuse me. If you want to raise the object 1 foot, you have to pull 4 feet of rope on the part where it says PA there. But so that's the trick of pulleys. Okay, so now we're on to compound machines. And what is that? A combination of 2 or more simple machines. And that's pretty much what all machines are. You can take the most complex thing out there, and if you take it apart, you will find that inside it's just a bunch of gears, levers, wheels, axles, maybe some screws. There's not much, there's not a lot of other things going on in there. So right there's a drill, an old-fashioned hand drill, and it shows you the different types of simple machines in there. The gear is another form of wheel. The lever is on the handle, the wheel and axle, so the handle can rotate. A screw on the tip. That's all there is to it. Here's where things get complicated, and I have some good news. We're going to ignore most of this. Mechanical advantage. That's where you measure the output force and the input force, and to see what kind of work your machine is doing. Mechanical advantage of levers. So if you push down with 5 pounds and you pull with 50 pounds at the nail, then it's 10 to 1. So that means that your length must be 10 times as long. So if the short part is 1 inch long, then the long part has to be 10 inches. If that doesn't make sense in this right here, right now, don't worry about it. 2 types of mechanical advantage. Ideal. Those are the kinds of things in a perfect world where we eliminate friction and think everything works perfectly. And then actual, because nothing is perfect. There's different types of mechanical advantage, and efficiency can be measured for machines. And efficiency is never 100% because you always have some friction in the system. And that's everything. Okay, so sorry that was so long. The homework will be much simpler. Thank you very much.